All right, polynomials. Let's start here. What do you guys remember about polynomials from last year? Forget about what you see on the notes in front of you. What do you guys remember about polynomials? Can you air draw a polynomial for me? What does a polynomial look like? Like, can you draw it in the air? Like, for example, a quadratic is technically a polynomial. You guys can all draw a quadratic, right? But draw me a more complicated polynomial. What do they look like? They kind of, they sort of like, they can be sort of wavy and they can have humps and valleys and stuff in them. Sometimes they do. I saw some of you drawing like a sort of like a little S-shaped thing. Sometimes they do something like that. Okay. What else do you guys remember about polynomials? Did you guys talk about zeros last year, or did you talk about roots of a polynomial? Or both? Or neither? Both zeros and roots? Yeah, zeros and roots are essentially the same thing. We'll be talking lots about zeros. Do you guys remember how to spot zeros of a polynomial on a graph? If I gave you a graph of a polynomial, do you know where you'd look to find the zeros of the polynomial? This is from our Algebra 1 assignment this week. Here's a polynomial graph. Do you know where you would look to find the zeros of that polynomial? On the x-axis, they're the x-intercepts or the zeros. Sometimes they're not on the x-axis because what can be true about zeros sometimes? They can be imaginary. Did you guys deal with imaginary zeros last year? Okay, that's a couple lessons away, so it's okay if this is all a little fuzzy. We'll be analyzing x and y intercepts of polynomials, which we should be familiar with because we know the rule for finding x and y intercepts from any function ever. It's just a matter of putting a 0 in for x or for y and solving. So let's talk about what we're going to do today. So today's goal, a couple different things I want you to be able to do. If you get a polynomial and it is in a nice factored form like this, I want you to be able to look at those factors, determine where your zeros are, what the multiplicity of those zeros are, and how that translates into what you see on the graph. Where does it cross the x-axis, and what is the behavior at that point? We're going to talk about end behavior, and this is where we'll learn our first pre-calculus dance move of the year. And then we're going to go on to the next page, and we're going to basically be doing the same thing here, except this one's in standard form, so we'll have to factor it first. And then we'll do all that same stuff that we just talked about. And then we're going to work backwards. I'm going to give you some zeros, and you're going to stick it together and make it into a polynomial. And then finally, to wrap up today, I'm going to show you how to use your calculator to find zeros if they're not nice, clean numbers. So if you guys remember the max and min function on your calculators and how we found those maxes and mins, very similar. Your calculator also has a zeros function in that same menu, and I'll show you how to use that to find the zeros of this polynomial. So that's what we got coming. It's quite a bit, so we're just going to kind of move through. So you guys are ready? Let's talk about zeros and x-intercepts and behavior. So I've broken this up into our 4 different factors here. To find the zero, we basically take the factor, ignoring the exponent on it, take the factor, set it equal to 0, and solve. So what would our 0 be for this one? If I set x equal to 0 and solved, I would get x equals 0. If I set x minus 2 equal to 0 and solved, I would get x equals 2 or negative 2. 2. If I set x plus 5 equal to 0 and solved, I get x equals negative 5. If I set 2x plus 1 equal to 0 and solved, are you guys able to do that in your head without writing out 2x plus 1 equal to 0 and going minus 1 on both sides and dividing by 2? Are you guys able to just look at this and say, it's negative 1/2? If you can go straight from a factor like this to negative 1/2, you don't have to show me these steps. If doing these steps helps you to find that it's negative 1/2, then by all means do it. But if you're able to jump straight from here to here, you don't have to show those steps in this class. All right, so how do we find a 0? We set the factor equal to 0 and solve. And that's why they're called zeros. They're called zeros because any of these numbers, if I plug them into this function, what's the entire function going to end up equaling? If I plug 2 into this function for x, what's this going to turn into? This factor here is going to be what? It's going to be a 0, and it's going to multiply by a whole bunch of other numbers, and the answer is going to be 0. So these are x values that will make the entire function equal to 0. That's why they're called zeros. All right, multiplicity is how many times that factor appears in your function. And we can find multiplicity by just looking at the exponent. So this first 0 has a multiplicity of 2 because that's x squared. X minus 2 is only a factor a single time. If it had an exponent, we would put a 1 on there. We usually don't. It has a multiplicity of 1. We can see that x plus 5 is to the third power, so it has a multiplicity of 3. And this 2x plus 1 would have a multiplicity of 1. All right. X-intercepts. The x-intercepts are going to be the same as the zeros unless the zeros are imaginary, but we're not going to have to deal with that for a couple more lessons. So for right now, x-intercepts and zeros are the same, except an x-intercept is a point. Don't tell me the x-intercept is 0. Tell me the x-intercept is 0, 0. X-intercept here would be 2, 0. Not 2. It's 2, 0. All right, and then let's talk about behavior. So I'm going to skip over this graph for right now, and we'll come back to that and graph it in a minute. We were talking about zeros. How do we find zeros algebraically? We set the function equal to 0 and solve. If we had a graph in front of us, how would we find those zeros? You guys told me this just a minute ago. We look at the x-intercepts. This is out of the textbook. This is kind of technical math jargon, but it says if I have a factor that's x minus c and it's to the nth power, then when I set this equal to 0 and solve, I'm going to get x equals c. So c is a 0 and the multiplicity is m. All right, we sort of talked about this a little bit last time. You guys remember when we were looking at graphs of like x to the second versus x to the sixth versus x to the 42nd? So the behavior, the main behavior that you're going to see for these x-intercepts, like, so this is like where the graph crosses the x-axis. The main behavior is, does it cross the x-axis like these three are, or does it touch and bounce off the x-axis like these ones? And the way we can tell is by looking at the multiplicity, whether the multiplicity is even or odd. So when we see a factor that has an odd exponent, that means that 0 has an odd multiplicity. We know that at that x-intercept, our graph is going to be crossing over from one side of the x-axis to the other. If it's an even multiplicity, we know that it's going to be bouncing off the x-axis. What might be a little bit new to you this year is how does it cross or how does it bounce? And like we talked about last class when we were looking at that x to the sixth, when it crosses, the higher the multiplicity it is, the more it sort of flattens out at the x-axis. So if a multiplicity is just 1, it's going to go straight across, but it's going to sort of start flattening out and make this S shape. The higher the multiplicity goes, it's going to become a more pronounced shape. If you had a multiplicity of 99, it would almost look like a sharp corner where it's crossing the x-axis. Okay, and then same thing for when it bounces. It just kind of becomes a little bit flatter at that point where it's bouncing off. All right. So we've got our behavior. Let's go ahead and come back up here and just talk about whether we're crossing or bouncing. Some people like to say touch instead of bounce, however you want to do it. So looking at the multiplicity, are we going to be crossing or touching at the origin here? We're going to bounce. We're going to bounce because that has an even multiplicity. We'll be bouncing off. How about we're going to have an x-intercept at 2, 0. Are we going to be crossing or bouncing here? Odd multiplicity will be crossing the x-axis. At negative 5, 0, again, odd multiplicity, so we'll be crossing the x-axis. And at negative 0.5, 0, odd multiplicity, again, it's going to cross. And this one's going to be kind of more of a S shape where it crosses, where these are going to just go straight across. So in a moment, we're going to come back and sketch this thing. But before we do that, I want to talk about end behavior. And actually, before we do end behavior, I want to do something to our original function. Does anybody have any questions about this table up to here? Okay, does this all seem pretty familiar to you from last year? The factors give us the zeros, the exponents give us the multiplicity, and then that multiplicity tells us how the graph's going to look at those x-intercepts. And again, we'll come back and graph this. We need one more key piece of information to be able to graph this thing. We need to know what's going on at the ends of the graph, so we know whether we're starting up here or we're starting down here, okay? And the way we're going to find that is we need to look at this equation in its standard form. So I'm going to change this into standard form, which would take a long time because I would actually have to sit and multiply all those factors out. So because I'm not interested in spending all that time, we'll actually be doing that in one of our examples on the next page. Not nearly this complicated, though. It turns out that really the only thing I need in order to find my end behavior for a polynomial is just the first term. I only need the first term of standard form. So if I could figure out what my first term is, going to be something x to some power. If I can figure out what that first term is, then I don't need to know the rest of this to figure out my end behavior. So I want you to think about, if I were to multiply out all of these factors, what would be the coefficient that would end up here? And what would be my exponent that would end up here? So to answer that question, you're going to need to be looking at all of the x terms that would end up getting multiplied together to make that first term. But keep in mind, some of them are being multiplied more than one time. So what do we think? What's our coefficient going to be? I got a coefficient of 1, right? Used twice, so 1 times 1. Keep this answer in your head. 1 times 1 times another 1 times another 1 times another 1 times another 1 times 2. Final answer, 2. So my coefficient is going to be a 2. Are we okay with why it's going to be a 2? I'm basically just multiplying the first term in each of my factors together. Now let's look at our powers. So I'm going to have x times another x. Keep track of where we're at now. And another x, but there's 3 of them here, so times an x times an x. I ran out of fingers here. Times an x. We're at 6, I believe. Times another x. 7? X to the 7. So I know that if I were to multiply all of this out, which would be extremely tedious, time-consuming, I know for a fact that my first term would be 2x to the 7th. You guys feeling comfortable about that? While we're here, let's use the same logic to figure out what the last term of standard form would be. See if you can figure out what would be the term at the end. So for this, I'm going to be looking at the last piece in each of my factors and multiplying those together. Now this one's interesting because it is the first and the last piece. So if I were to multiply x times x, I know we're going to have an x squared there. That's the only x that appears in my last term. All right. this is going to be a little bit trickier. Feel free to use a calculator if you need to. What's negative 2 times 5 to the third times 1? 5 to the third. 5 to the third power is 125 times negative 2 would be negative 250, and times 1. So it would be negative 250 x squared would be our last term. That was just for fun. We didn't need that. But that will come up later on. So what we're doing here is we're just predicting what this thing would look like if we were to write it out in standard form. All right, why do we do that? We did that because I needed this information here to know what my end behavior was going to look like. This is where we're going to learn our new dance move, guys. Okay, this is going to be super awkward and embarrassing, but we're all gonna do it together, because being embarrassed is less embarrassing when you have some buddies to do it. Are you guys ready? Okay, so there's kind of 4 different moves that you can make for your end behavior. So you guys with me here? Nobody's too cool for this, all right? Okay, so I want you to take your left arm, and it's going to go down, and your right arm's going to go up, okay? This is the move when you have an odd degree and a positive lead coefficient. It looks like this, okay? Odd degree, positive coefficient. Now, if I make that coefficient negative, what happens when we multiply something by a negative? Boom, it just flips over. So now it's a negative coefficient, odd degree. Okay, still odd degree, switch it back to a positive coefficient. All right, back to a negative, back to a positive. Okay, now what happens if we switch to an even degree? It's going to be going up on both sides. So here's even degree with a positive coefficient, but we make that a negative coefficient and we go, boom, back to a positive, odd degree, negative odd degree, even degree, negative even degree. All right, so that's our end behavior, okay? That tells us what the graph's going to look like on the far sides of the graph. So if we have a positive coefficient and an odd degree, we know it's going to be going down on the left and it's going to be going up on the right. This is end behavior, so it doesn't matter what's going on in between here. It could have a million little peaks and valleys. This just tells us what's happening at the far ends of the graph. So odd degree with a positive lead coefficient is going to look like this. With a negative lead coefficient, that's just going to flip over, and it's going to be going up on the left and down on the right. And again, whatever's going on in here doesn't really matter. The key is what's it doing at the ends. Okay, and then with our even degree, if it's a positive lead coefficient, it's going to be going up on both sides. We change that coefficient to a negative, and it's going to be going down on both sides. So when we do our next tests, I'm going to know when you guys get to number 7, because you're all going to be sitting in your seats doing this, okay? Maybe not. We'll see. All right, and I'm sorry I couldn't get that to you before homecoming. It would have been all the rage, but that's all right. Prom's still coming up, and we'll have some other dance moves before then. So, okay. Now we have everything we need to graph this thing, because now I can look at this and we can determine what our end behavior is. So we've got an odd degree and we've got a positive lead coefficient. So show me what's our dance move for this one. Odd degree, positive coefficient. We got this thing. So we know that it's going to be going on the edges of this graph. It's going to be going down on the left side, and it's going to be going up on the right side. That doesn't tell us anything about what's going on in between. It just tells us that eventually that's what the graph's going to end up doing at its furthest reaches. Okay, that combined with the information we've already found from our zeros is going to allow us to make a sketch of this thing. Can you guys go through and draw some points on your x-axis for each of these intercepts, please? We've got one at 0, 0, 2, 0, negative 5, 0, and negative 1/2, 0. All right. What we're going to do now is we are going to build our graph, and we're going to build our graph from one edge to the other. Do you guys want to start on the left and go to the right, or do you want to go backwards? Left to right, like we read a book? That's fine. Yep. It doesn't really matter. We pick one edge and we just go from there. So what do we know? At this edge, I know I'm going to be going down because of our end behavior. Because we saw in our standard form we had an odd degree and a positive lead coefficient. So as we move to the right, my graph's going to need to rise up to meet this x-intercept here. Now let's think about this before we start drawing this in. Tell me, what is going to happen when I get to -5? Is my graph going to cross over the x-axis, or is it going to bounce off? It's going to cross over, and we even said it was going to sort of make a little S-shaped when it crossed over. So let's rise up. We know it's going to have to hit the x-axis there at some point, and it's going to cross over into positive territory there. All right. All right. As we continue moving to the right, eventually my graph is going to need to come back down to the x-axis for this intercept. There's no others in between, so we know it's not going to be touching or crossing anywhere in between. But eventually it's going to come back and hit it at -1/2. And what's it going to be doing when it hits at -1/2? Is it going to cross or bounce? We said it was going to cross. So I don't know how high up this thing goes. I don't know if there's any wiggles or anything along the way, but I do know eventually it's going to come back down, and it has to cross here because we said that was, well, we said that was going to be the behavior at that intercept. All right, moving to the right, eventually we're going to have to get back up to the x-axis, so we'll have to turn around and come back up. And when we hit at 0, are we going to cross or bounce? 0, 0, we're going to bounce. So we're going to be kind of moving back up to hit that x-intercept. We're just going to bounce right off, and we're still in negative territory on the other side of that. And then finally, we got one more x-intercept. I'm really hoping that when we get to this one, we're going to cross. Because that's the only way I'm going to get from down here to meet up with this end behavior that we already knew was happening. Are we going to be crossing it too? Please say yes, please say yes. Yes, we're crossing it too. That's good, because that puts us on the right side of the x-axis to be able to finish up our end behavior over here. Now, is that exactly what this graph looks like? No, no. You type this into your calculator and you're not going to see something that looks exactly like that. However, you will see it crossing and bouncing at those particular points. Just for fun, let's go ahead and type that in. I would do it myself if I could find my calculator. Give me a minute to search here. I'm a little curious where that ended up. I had it yesterday. Anybody see a pink calculator laying around? Yeah, do you mind if I borrow yours for a minute? Thanks, appreciate it. Might be in the math office. All right, let's see here. What do we got? I'm going to just type in the version that we got. X squared, x minus 2, x plus 5 to the third, and 2x plus 1. Now, I've graphed enough of these things that I'm not guessing that I'm going to be able to see where these things top up and where they bottom out. I'm guessing I'm just going to probably see, it's probably going to look like a bunch of vertical lines. Is that what you guys are seeing when you graphed yours? So if I go, I'm going to do zoom 6 to make sure I'm on my standard zoom. So yeah, that looks a lot different, but I can kind of see it crossing here. You can sort of see it bouncing right here. And crossing here. If I wanted to adjust my window, and this isn't important, but if I wanted to adjust my window and make my Y max, say, go up to 100 and down to -100, that might show me a little bit more of, I still can't even see. How about -500 and +500? Still can't. Anyways, it's starting to look a little bit more like a polynomial. The main thing, though, is are we able to figure out where it crosses and what that behavior is? Are you guys feeling pretty comfortable with that? Excellent. Quitting out of this, getting you back into standard zoom. Okay, thank you very much. Okay. That's bothering me. I hope it didn't walk away again.